Hello, everybody. Welcome to today's webinar. I just wanted to make a quick sound check before getting started. So if you can use your panels, it can be in the questions or in the chat window. Just tell me if you can hear me well, and we'll get started right away. Perfect. Well, I see several people. Several of users are connected. Welcome, everybody. Happy to see you back. So I think you will like what you'll see today in the webinar. So feel free to use the questions panel to make your questions. We'll try to answer at the end most of the questions I get. So thank you so much. Let's get started. Hello, everybody. Today's webinar, it's about advanced modeling of overland oil spills from wells, tanks, and pipelines, considering heat transfer. My name is Reynaldo Garcia. I'm the Director of Model Development and Applications at Hydronia and Hydronia Europe, and I'll be presenting the webinar today. The webinar outlines includes a first part where I briefly discuss why it is important to consider heat transfer in oil spill simulations, particularly oil spills overland. Then I will discuss about the basics of overland oil spills modeling, the capabilities of the existing oil flow 2D model and the new features. And then I will do a short overview of some results of an actual oil flow 2D application of a tank spill. And if you have any questions, you are free to use your question panel and ask your questions there. We'll try to answer either during the webinar or after the webinar if they are general questions. Thank you. First, it's important to acknowledge the help of many people who had contributed to the generation of all these amazing tools that we are showing to you today. As you can imagine, these complex models would be impossible for a single person. So we have a great team that make possible all of these developments, especially with the agreement Hydronia has with the University of Zaragoza, led by Pilar Garcia Navarro, and they're all amazing team of people. And also Hydronia, that it's a really great team that is all the time doing new things and improving what we have and what we can offer to all of you. Of course, I need to acknowledge our several users that we have, not only for oil flow 2D, but also for river flow 2D. And they have significantly contributed to the advancement of the tools and also in many applications and projects that they have been doing over the years. So why it is important to consider heat transfer, and particularly how the changes in the temperature affect the oil behavior and the oil flow. Well, I'm presenting here two charts. The left one indicates the variation of density, and this is the density curve, how it varies with temperature. And also this blue line indicates how the viscosity of the water varies with temperature. And as you can see here in this chart, there is a very slight variation of viscosity and density with temperature for water. That means that the impact of the changes in temperature, of course, if we get to very low temperatures, to the freezing point, then of course we're changing significantly the water properties. But provided we are above that level, the oil properties are essentially unchanged or very little in terms of the impact that they can create on the water flow. That's why in most applications of inundation or flooding related to water, temperature is not a factor that is of significant contribution or that should be considered. Now, it's a very different thing when we deal with crude oils, and there are many applications where we need to assess where the oil is, how the oil behaves when it's spilled on the surface of the terrain. But as you can see here, this is for a particular oil, and you can see here how the density can vary, but more significantly, the viscosity can increase by actually an order of magnitude as the temperature decreases. So the lower the temperature, the higher the viscosity, and that increase can affect the flow of the oil. And that's one of the reasons that we need to consider the heat transfer and how the heat transfer affect the temperature, and in turns how the temperature affect the viscosity and density of the fluid. Now you can see here that this variation, but the thing is, in many oils, the outflow or the storage of the oil or the transport temperature is very different from the ambient temperature. For instance, some oils need to be stored at very high temperature in order to make it flow, or they have to be heated in order to make it flow in pipelines, or their own temperature in the reservoir is much higher than the ambient temperature. So when the oil, if there is a blowout of a well, that oil temperature is coming much higher than the ambient temperature. So when maybe the outflow is about 60 degrees centigrade or even higher, and as it gets in contact with the environment, that temperature will decrease in time as it flows over the surface, and then the viscosity and density will increase during that process. So that's the main physical description of what's go on. Now there are many other factors, and one of the important factors is that in some oils the pour point is very high. That means that the pour point is temperature at which the oil will start to flow, or in other words, the temperature at which the oil will not flow anymore is the limit. And that has a relationship with the yield stress that is used in many non-Newtonian fluids. So if you have an oil, if you're dealing with an oil that has a high pour point, then when the temperature of that oil gets below that pour point limit, then the oil will not flow anymore. So let's say you have this oil. This is it's a yield stress with respect to temperature. So you can see here that for high temperatures, the yield stress is very small. That means that there will be no resistance, or that fluid will not require an initial stress or initial force in order to get it moving. But as the temperature decreases, at some point you may reach the pour point, and below, for temperatures below that pour point, the yield stress is extremely high, and for these extremely high yield stresses, the oil will not flow simply anymore. And as you can see here with this data, which is from an actual oil, the temperatures that corresponds to this very, very high yield stress are sometimes above the ambient temperature. So that means that if the ambient temperature gets to these levels, then the oil will not flow anymore. And the same applies with the viscosity. The viscosity will mostly affect the speed of the flow, how you know, how far and when it will get to different locations. So it affects the combination of factors of the temperature with yield stress, changing yield stress, and density and viscosity will affect how far will the oil get, and secondly, how fast will it get to the different locations. So in terms of the overland spills, the main purpose of using a model to represent the oil spill is to determine the affected area that it can be impacted by these spills. But it's very important to determine where is the oil going after a given spill and when it's going to get there. And in those terms, it is where it is critical to determine the correct changes in properties based on the temperatures that could be in the environment. The other thing is that one of the factors that affect this type of simulations or the use of oil models in overland flow is that when you need to assess when or if the oil is going to impact what is called high consequence areas or sensitive ecosystems, sometimes the area have some urban components, maybe in a city, or it may be in a town, or it may cross, you know, some lands that have crops or roads or different components that need to be accounted for in the model. The other thing that is important is that the oil spills do not always occur in the same way. They based on their origin. Sometimes they occur due to well blowouts. Sometimes they occur to burst in pipelines. And sometimes they occur in tank breaks. So you have a storage tank and you need to assess the containment of that storage tank in case of the tank fails, and you need to see where the oil is getting to. Now, in all of this application, we have found that and for many oils, considering the dependence of the yield stress, viscosity, and density on temperature is crucial in estimating the runout distances. So, and I will go to show you some results that I think illustrate how this can affect the model results. Now, some simulation challenges that we face when dealing with this type of flows is that the terrain is very irregular. So we are dealing with something that cannot be idealized with a 1D model, or it cannot be idealized with a simple, you know, square grid model. You need to represent realistically the terrain if you want to have accurate results. Also, the flow is viscous with a free surface and sometimes non-Newtonian, as we discussed previously. And of course, the properties, as we have seen, can change during the spill. Based on the variations of temperature in the environment and on the oil itself. The spills can occur rapidly and with very high velocities. And you normally need to deal with many scenarios in order to make a reasonable risk assessment. Now, the oil flow 2D model that Hydronia has developed over the last few years includes what is called now a basic model. That basic model does not have or does not consider heat transfer and includes the solution of 3 equations, the continuity equation or mass transfer equation, and 2 momentum equations, which are the typical shallow water equations that applies to viscous flow, because this stress term actually represents the viscous fluid, as I will show you. And these equations are solved by a finite volume numerical solution that is very important because it ensures that the conservation error, the mass conservation error, remains almost 0 all the time. So the numerical solution is not creating or eliminating any mass of the oil. The basic computational unit of the model is a triangle, and in the triangle, the model computes the velocity and depth of the oil. And this computational triangle is part of a triangular irregular network that can be adapted to any surface or any environment with obstacles, houses or streets or any other feature in the terrain. The model also included the consideration for non-Newtonian fluids, fluids that can vary in viscosity or can show a yield stress. And that stress terms that I showed you before in the equations could have a yield stress and also a viscosity term that represents a fluid that is not similar to water. It can vary in viscosity, it can have a much higher viscosity than the viscosity normally that you consider in a shallow water model for water. The rheological formulations that are available in that basic model include the full Bingham, simplified Bingham, and quadratic model. They can consider the typical behavior of most crude oils. And one of the things that we added, recognizing that the oil properties could vary significantly with temperature, for that basic model, we consider temperature dependence that could represent how the viscosity and density could vary with temperature, assuming yield stress constant, but with a prescribed temperature variation during the simulation. So we didn't have an equation that could consider how the oil temperature would change, but that temperature was prescribed by the user essentially. And also we have some other processes that can be important in oil flow, which can include the evaporation of the oil and also infiltration in the soil. All of this was included and remains included in what is called now the basic model. But now we have a heat transfer model that I'm going to also discuss. So the basic assumptions in the basic model, as I mentioned, includes that the oil temperature, density, and viscosity can vary in time in a prescribed way defined by the user, but remains constant in space. That means that the oil and density depend on that prescribed temperature, but they vary simultaneously in the complete mass of the oil. It's not a gradual process. It's just a process determining how you, as a user, prescribe that change. Also, the assumption was that the yield stress remains constant in space and time, and consequently, the wind speed, temperature of the air, relative humidity, or solar radiation play absolutely no impact on the results or the oil properties. So the model could not assume that you have a spill that can last several days, for instance, and you have flow overnight that could cool off the oil, and then during the day, the heat transfer due to the solar radiation would change things for the flow completely. And all of this was packed in a GPU code that can run significantly faster than the standard CPU code. And we have talked that in other webinars, but I just wanted to mention here that the latest cards that are available, like the RTX 3090, can now handle more than 10,000 cores with a memory 24 gigabytes. So this brings the opportunity to solve real big problems in a very short time. Now, in terms of the new model, what are we adding to that new model? As you remember, in the past, in the basic model, we had the mass conservation equation, the two momentum equations. Now we have a third equation. Actually, here's in one dimension, but it's actually in two dimensions. But it accounts for a source term that represents the flow of the heat from the oil to the atmosphere and soil, and also from soil and atmosphere to the oil. So that interaction is considered in this source term, and this is the heat flow. This is the oil density. This is the specific heat, and this is the oil depth. And this is oil all changed in time. So we have the full variation of temperature in space and time. And to close these equations, we need one that represents how the viscosity depend on temperature. And this is one of the equations that we provide. We can also account for a variation based on a table that the user would provide for specific oils. And what this implies is that we have now the possibility to consider the heat transfer as a function of the wind speed, the air temperature, the relative humidity, and solar radiation, and how those changes in temperature will affect the oil properties, such as density, viscosity, and yield stress. So the main assumptions of the new model include that the oil temperature, density, and viscosity, and yield stress now can vary in space and time, and they are dynamically calculated by the model for the specific properties that you provide for the oil. The wind speed, air temperature, relative humidity, and solar radiation can vary in time. So that means that you prescribe for the period of simulation what scenario you want to consider. Although assumption is that normally these spills occur over a relatively short area. So we are assuming that there is no variation of these properties in the space. The model allows different options to account for fluid properties dependent on temperature that normally provided for specific crude oils. And all of this is included, as it was before, in the oil flow to the QGIS user interface. Now, the typical oil spill simulation workflow, it depends on if you are using it to represent a spill from a storage tank or from a pipeline or from a well. But normally you have common steps like open the QGIS model, creating a new oil flow 2D project, load the terrain elevation, load an aerial image or the background image from Google Earth, draw external polygon, assign the spill location or locations, define the initial conditions, set up the run parameters and run the model, and then prepare basic results. Just to summarize this in the example that I'm going to present to you today, this is an area, this is an urban area. Unfortunately, for the confidentiality reasons, I cannot present to you today actual projects that we have done with the model. So I built this example for you, which is a kind of illustrative model. It's not an actual spill that occurs, so I'm not releasing any confidential information that would compromise or agreements with different companies. So this is actually an urban area in South America, in Venezuela. And it happened that we had this high resolution terrain It's a raster terrain that includes an urban area with streets and buildings. And it had a complex terrain, so it occurred to me that it was an illustrative example to show you the capabilities of the new model. So this is the terrain. This is a polygon that represents the boundary of the area that we are going to be focusing on. And the example includes the break of storage tank that would be on this upper side of the mountain here. And as you can see here, this is a detail of the tank. So we have the tank represented by a weir, which is one of the components in the model. And the assumption is that we have a break here, and this is an opening that would be caused by a burst of the tank. And we have an initial oil elevation within the tank that corresponds to the actual storage capacity of this tank over here. So what we want to see is what happens if the tank bursts in this location here, and how the spill flow can change in terms of the new heat transfer component, on how that can affect the results. So for that purpose, we generated a mesh that is shown here. The colors indicate the elevation of the terrain. Actually, the red is the lower elevations, and the bluish colors indicate the highest elevation. So this is higher. The flow will occur from here to downstream here. And you can see here that we are included in the mesh, the inside of the tank. So this will allow us to not imposing any discharge. So we let the model calculate the outflow from the tank and not imposing a value here. We could have used the source component to do that and impose a hydrograph that would represent how the volume of oil will be released. But for this example, I choose to use the model to calculate directly that flow. So I'm not imposing any flow here. I'm just imposing the initial conditions within the tank. And as the oil flows, the model will determine that discharge coming out of the tank and into the urban area downstream. So the other thing that I wanted to show you is that the mesh is fine enough to capture many of the features of the terrain and urban area. As you can see here, we have some features in the terrain that are accounted for with a flexible mesh. One of the advantages of the flexible mesh is that you can have break lines that force the mesh to adapt to all these complex features, and that's very convenient in many applications. So once you have the mesh created in the QGIS plugin, then you enter the parameters that will represent the actual oil spill and oil behavior. So you need to enter environmental parameters. You have this new oil spill on land environment here, where you enter in different tabs, different data. For the environmental parameters, you select the resistant relation, but also the initial oil temperature. This will be the initial temperature that the oil will have within the tank. The heat capacity, and then the environmental parameters that include the wind velocity, relative humidity, temperature, air temperature in this case, and solar radiation. See that the solar radiation can change in time. Actually, all of the parameters can change in time and can be user defined. Then the density, we have two options. The one option includes a formulation that represents how the density vary with temperature based on some constant here. But you can also add your own temperature density file if you have that data. You can do the same for viscosity. You can use an existing viscosity formula. This is an exponential formula is quite accurate for many oils. And but you can also enter your own temperature viscosity file. For the yield stress, in this case, we are using a table that represents the variation of the yield stress for a particular oil with the yield stress with temperature. And then you can also set some constants for the evaporation of the oil. I just wanted to mention that, so once that it's set, you just run the model, but we have an option that we haven't discussed here because we are using an initial elevation for the spill. But if you have multiple sources, you have an option that you can use for multiple sources batch run that automatically will run dozens of as many sources that you may have, which is handy for spills coming out of a risk analysis of a pipeline that have sometimes thousands of runs that to make. So this batch run automate the process, and this has been there for some time, but we have been improving that in the latest releases. Okay, so let me show you some results to complete today's webinar. What I wanted to show you, I was thinking, what would be the best way to illustrate the importance of considering heat transfer and the impact in oil properties. So bear in mind that I'm using real data of a real oil. So I'm not making up any specific behavior of the oil in terms of density and viscosity. So this is real data of an actual oil. And what I'm showing here is that the colors will indicate the depth. These will be two animations. One where I'm changing a single parameter. The single parameter is the wind speed. So as you can imagine, the wind speed will change the heat transfer from the mass of oil to the environment. And the higher the wind speed, the faster the exchange of heat between the oil and the environment, and of course the faster that the oil properties will change. So this is what happens with the oil transfer model, but considering a wind speed of 2 meters. Let me start the So essentially, the oil starts to come out of the tank. The tank is almost empty now. At the end of the simulation, it's about half an hour. And as you can see here, the oil gets through the streets of this urban area and gets to the final site of this location. So the run at the right, the only difference, as I said, is only an increase in wind speed. So it will be an assumption that there will be a very low wind speed, and this will be a situation where the oil will occur at a moment where the wind speed was very high. This is what happens. That's it. So the model simulated this flow of the same oil, but at a situation where the wind speed was 20 meters per second instead of 2, and the oil didn't move anymore. So why didn't move anymore? Because the properties changed and the oil viscosity went rocket high, and also the yield stress. Let's see what happened in terms of the temperature in these two cases. So this graphs here, or this animation, show the oil temperature. See that the oil temperature initially here was 55 degrees Celsius here, and the ambient temperature was about 25. So you may see some cooling although you see the cooling is very slow as it moves. Remember, this is about half an hour. So there is some cooling here, but still you have very high temperatures most of the distance. So this is what happened with 20 meter per second wind speed. See, even the oil stopped, but it still is cooling. Let me repeat it because I think it's interesting. You see how it's cooling? The lighter temperatures is cooler, and it's still cooling in this even after it is stopped. So how did temperature affect the yield stress? So the yield stress in this case is the one responsible for stopping essentially the fluid. As you can see here, the lighter colors will represent the higher yield stresses. So let me show you the wind speed 2 meter per second simulation. See, darker colors, very low yield stress, very fluid. There are some areas where it's much cooler here that are stopped or with very high yield stress. But let's look at what happened with 20 meter per second. You see how the yield stress increases? Let me repeat it. On the boundary, you have a higher cooling, and then it's sufficient to stop the oil because of the very, very high yield stresses. So at the end, everything is so viscous and the yield stress is so high that the oil stopped. Let's finally look at what happened with the oil viscosity. Here, the darker colors indicate the higher viscosity. You see here that the viscosity remains relatively low, except from the areas on the top or near the tank. And this is what happens with the wind speed 20 meter per second. So the viscosity increases as the time passes, as the fluid cools. And you can see that at the end, what this represents is that the initial assumption that the oil would get to very far locations from the tank spill was not accurate because not was accurate, it was much lower at the wind speed of 2 meter per second. This is what would be probably similar to what if you would assume that there was almost no variation in our oil properties. So you see how big is the dependence of the oil on the environmental parameters for some oils. It's true that there are some oils that are so light that they would not see a big affectation due to the changes in temperature or properties, because the properties will not be so dependent on temperature. But it is important that in several fluids, in several assessments of risk of crude oils, this could be a very important thing to consider due to the fact that they can represent big changes in the area that is impacted. Okay, so just to conclude, just a couple of remarks. The behavior of some crude oils require considering the variation of the fluid properties during the spills. That's a very important thing. What I was thinking is that, if we have already the option of using heat transfer, there is essentially no need to guess if the heat transfer will be important or not to your simulation, because it will be the actual data that you have for the fluid and the model that will tell you the results, the actual results. So if this model is available, then there is no need to go back to a basic model because that would give you no advantages at all. That's why modeling heat transfer in Overland fluid simulations can improve the prediction of impacted areas because they will consider something that actually occur in reality. And the new oil flow 2D heat transfer component is a unique 2D model. And I stress here the unique because to our knowledge is the only two-dimensional oil flow model with a free surface that consider heat transfer and the variation of temperature in such a comprehensive way. And in that way, it can contribute to better assessments of oil spill impacts. Well, thank you very much. That's all I had for today. If you want further details, you can use my email me, feel free to email me and ask any questions. And also, if you have questions now, I will be happy to answer before the end of the one.
Well, I do have some questions. We have been answering some of them. But let me, for the sake of the benefit of all the audience, just reiterate some of the questions that that may be of interest to others. There are several questions related to database. We do have a very limited data for many oils in the model. I have pointed out to some of you that we do know about several public available databases that give the data that you would need to a model such as this one. For instance, that report on the variation of viscosity with temperature or density with temperature. Yield stress is more rarely available in public databases. What we have done in some of the projects is that the client or the operation company that extract the oil, they provide the data for the yield stress or the pour point. At least pour point may be a proxy at least to understand if you have an information about the pour point of your oil, you can at least have an approximation of how the yield stress will change with temperature. But we are moving in that direction in terms of development in the model. We're planning to include in the future version some databases that are specific to the data that we require in the model. We have questions also related to the availability of this new tool. I wanted to mention that that tool will be included in version 7.51 that is going to be released next week. Version 7.51 includes all the capabilities that I discussed, and that will be free to every user that has updated that is current with the maintenance. So that has essentially no cost to any user that is current in the maintenance. So we don't provide updates or upgrades at a specific cost, so it's included in the maintenance cost essentially. I have also questions related to let's see, let me read because I have a bunch of them coming up. I have a question related to the dependency of the results about other factors like relative humidity, wind, or other factors. So from the test that we have run so far, we see that the wind speed is an important factor. So the results are sensitive to wind speed mostly, and solar radiation, of course, and ambient temperature, of course. Relative humidity also plays a role. Probably it's not that important with respect to solar radiation or wind speed. Solar radiation definitely has a very important factor because as you are aware, solar radiation varies during the day, but it goes to zero during the night. So if you have a spill that lasts for several days, what you see in the simulations is that the yield stress goes up and down, night and day, and that so a flow that has stopped during the night may restart during the day because of the increase in temperature. That's a very interesting thing that can happen. Yeah, but let's see. I have all the questions here. Kelsey asked if she says, I would be interested in a comparison between a high resolution surface versus a low resolution surface. So 2 centimeters versus 1 centimeter resolution versus 1 meter resolution. Well, yeah, well, that would be, unfortunately, we don't have that kind of resolution in this particular example. It depends on the mesh, of course. You would need to have a very fine mesh. I don't think that is sensitive. We haven't gone so high to a 2 centimeter resolution, but we have done analysis of resolutions that range from the 1 meter to 20 meter. And it highly depends on your surface. If it's a flat surface, it's one thing. If it's a very mountainous, mountain terrain, it's different thing. But in the bottom line here is that you will need to do your own convergence analysis for depending on the terrain that you have. But I don't think you need to go to 2 centimeters in order to get good results at all. At least from our experience. Well, I guess, yeah, I have another question about the availability of the model. I think I answered that already. I have a question here. Does Overflow 2D consider heat transfer between oil and water if it reaches a water course? Well, we have a separate model for oil spills on water that links to this one, but it's not the same model. We are developing now a model that it's a 2-layer model that will simulate simultaneously water flow and oil flow. Again, it's under development, but it's a model that will represents that kind of situation where the flow can occur over water. What we do so far, now what we can do now is that we model up to the interface with the water body. We extract the results from the overland flow model, and then we input that volume or that hydrograph, the flow rates from the oil coming to the land and then into the water flow model. So they are essentially two different separate models that need to be applied now until the 2-layer model. It's a very complex model, as you could imagine, and it will take some time. Will certainly not be available this year. I have another question here. Does the model work only in dry environment or in the wet, rainy, or river discharge environment? well, I guess this is related to the previous question. Incidentally, this model accounts for rainfall, but rainfall of oil. And some people say, well, rainfall of oil, what's that? Oil doesn't rain, right? Well, it does sometimes, and we have used the model in that way in some projects, and some clients have used it too. If you have a well blowout, if you have seen a well blowout, you have seen that you have a jet of oil that goes to into the air, up in the air, and then it comes down as a rainfall around the well area. So the rain component of the model is handy for that, because you can give the oil properties, and the oil, instead of having a single point outflow, it actually rains within the well area. And you can select a polygon or a circle around the well area, and then you will have a more realistic inflow of the oil blowout into the model. However, it's not, the model cannot, in what has as it is now, it cannot account for the simultaneous occurrence of a rainfall of water or a water flow and its interaction with the oil flow. As I indicated before, the way that you can use it is you model separately the oil flow, and then when you see that the oil gets into the water, you let it go, but it will not interact. You create a cross section so that you can extract the flow hydrograph from the Overland flow oil flow model, and then you input that into the other model that we have that we haven't discussed it today, but it's the oil on water model. That is a separate one. So that's how we can do it now. Well, we consume our time. I have to stop it here, but I just wanted to thank you for your time and interest in this model. We are really excited about the capabilities of this new tool that is will be available next week. And feel free to ask me any questions if you have, and share the link that you will get with the video probably in a couple of hours. You will get the video link, so you can free to share it with any of your colleagues. And if you have any questions or requests for future development, we are also open to hear that from you, and to work together to improve this tool in the future. Thank you very much.